Welcome to the deep dive. Today, we're taking a bit of a shortcut.
Yeah, bypassing some of the heavy math.
Exactly. We're diving straight into the, let's say, fundamental strangeness of the universe.
Mm-hmm.
Our main source is this really cool physics allegory, Alice, in Quantumland. It personifies the rules of quantum mechanics.
Which is a great way to approach it. Our mission here is really to give you the essential grasp of the subatomic world.
Because, let's face it, the language needed for atoms, nuclei, quarks, it just completely breaks our everyday common sense, doesn't it?
It really does. Your intuition, built on, throwing balls or watching planets.
Newtonian physics.
Right, classical stuff. It works perfectly for big things. Apples falling, planets orbiting, all that.
But then, early 20th century physicists start poking at electrons, looking closely at light.
And that whole classical framework just falls apart, shatters, like you said.
Yeah.
And the truly wild thing about quantum mechanics, QM, is that its concepts are bizarre particles in multiple places, but its predictions
Are spot on. Incredibly precise.
the most precise in all of science, actually. Like the electron's magnetic moment, calculated versus observed.
They match out to how many decimal places?
10 significant figures. It's astounding. Classical physics can't even get in the same ballpark.
Wow. Okay, so that level of precision, predicting reality down to the 10th decimal place, it basically forces us to accept these rules however foreign they feel.
We don't really have a choice if we want to describe nature accurately.
Okay, let's unpack this then. Let's start where Alice does, kind of,
Hmm.
in the realm of quantum finance. The Heisenberg Bank.
Ah, yes, the bank, where energy is the currency, usually measured in electron volts, EV.
And the bank, it seems, is constantly dealing with these virtual particles.
That's a good way to put it. They're like the universe's little loan sharks. They're virtual because they don't quite have enough energy.
The rest, mass energy.
Exactly. They don't have the minimum needed to just exist stably on their own.
So they borrow it. They take out these tiny energy loans to pop into existence for a moment.
That's the core idea. And the whole loan system is governed by the Heisenberg uncertainty principle.
The energy time one, right?
Specifically that one. The uncertainty and energy, delta E, times the duration of the loan, delta T. It has to be around this tiny number, A, Planck's constant.
So the equation is like the strict bank teller.
Pretty much. It sets the rules.
Okay, so if I need a big energy loan, say I want to create a pair of really heavy exotic particles,
Highly dressed, as the book calls them, yeah. Massive credit needed.
then the time I get to exist, the loan duration, has to be super short.
Extremely short. The repayment is due almost instantly. Heavy particle pairs vanish much, much faster than lightweight ones.
That's a universal rule.
Absolutely fundamental. More energy borrowed, the quicker the universe demands it back.
It sounds like this quantum economy is incredibly frantic, happening everywhere all the time, but super brief.
It is, and it's crucial. It means even in what we think of as empty space, a perfect vacuum, there's this constant churning, particles popping in and out of existence. So while, over the long haul, energy is conserved in the universe, in these tiny fractions of a second, thanks to quantum fluctuations, reality can essentially borrow energy from almost nowhere.
Okay, that's mind-bending already. So moving on from the bank, Alice meets the regulator. This is about possibility. Choice.
Exactly. If the bank is about what energy you can borrow, the regulator's office lays down the laws about where you can go, what paths are available.
And this is where we hit a really foundational quantum principle, the logic for how things move at this scale.
Yes, Alice finds this rule posted, written in this ancient quantum script.
Which translates to something incredibly blunt.
Yes,
Everything not forbidden is compulsory.
compulsory,
Yeah.
which is just radically different from our world.
Yeah, classically, if you have two ways to get from A to B, a ball takes one path. Simple.
But in the quantum world, if a particle can take multiple paths,
It doesn't choose.
it doesn't choose, it takes all of them simultaneously.
Right, that's superposition. The particle exists across all possibilities. If there are three doors, it walks through all three at once. That sounds amazing, but how does that, show up in the real world? How do we see that compulsory exploration happen outside the usual double-slit example?
Well, it manifests through something called probability amplitudes. Think of them as possibilities, but with a phase, like a wave.
Okay.
The total state, the reality of the particle, is the sum of all these amplitudes for every single path it could possibly take.
And the magic happens when these paths, these amplitudes overlap.
That's where interference comes in, just like water waves.
Right, waves can add up or cancel out.
Exactly. where the amplitudes combine constructively, peaks meeting peaks, they reinforce each other. That means a high probability of finding the particle there.
And where they combine destructively, peak meets trough.
They cancel out completely. Zero probability. The particle will never be found there.
So the particle genuinely explores everywhere it could go.
Compulsorily.
But where it ends up, where we detect it, is determined by the interference pattern of all those possibilities.
Precisely. The wave-like behavior maps out the probabilities, but when you actually look, you find a single particle, a quantum, in one specific spot.
It explores like a wave, but arrives like a particle.
The ultimate quantum paradox. It has to explore all paths, but it has to be detected as one thing.
Which leads us straight into the biggest headache in quantum theory, right? The measurement problem.
Oh, yeah.
The century-long debate. If the quantum world is this big soup of all possibilities existing at once, superposition, why do we only ever see one single definite result when we measure something?
Where does the other stuff go? What happens to all those parallel paths, those other possibilities? And, well, the sources lay out the three main schools of thought, the big answers, though none of them make everyone happy.
Okay, let's take them one by one. First up, the standard one, the one you usually learn first. Copenhagen interpretation. Bohr, Heisenberg.
Right, the orthodox view. It's pragmatic, maybe conceptually a bit unsatisfying for some.
How does it work?
It basically says the act of measurement itself causes the change. It forces the wave function, that collection of all possibilities, to collapse or reduce.
So the amplitudes for the outcomes we didn't see just vanish instantly.
Gone. Think Schrodinger's cat. Before you open the box, the cat is in a superposition. Alive and dead.
Right.
The moment you measure, you open the box, boom, reality picks one. The wave function collapses into either a live cat or a dead cat.
But what is a measurement? That's the fuzzy part, isn't it? Where's the line between the quantum thing and the classical measuring device?
Exactly. The theory doesn't clearly define it. That's the big conceptual problem with Copenhagen for many physicists.
Okay, what's the next contender? The Emperor's theory. Sounds a bit grand.
It is. This one puts consciousness right at the center. It suggests the collapse only happens when a conscious mind observes the system.
Wait, so the Geiger counter clicking isn't enough?
Not according to this view. The argument goes, the Geiger counter itself is made of atoms, right? So it should also be part of the quantum system, existing in superposition.
Until a person, a conscious observer, looks at the counter.
Yes. The idea is that the conscious mind is somehow outside the normal laws of QM, and it's what forces reality to become definite. It's controversial, to say the least.
I'll bet. Okay, third option. The Little Mermaid's theory in the book. The multiple worlds interpretation.
Ah, many worlds. Everett's idea. This one is maybe the most mind-blowing or extravagant, as the source puts it.
What's the core idea here? No collapse.
Exactly. It says the wave function never collapses. Instead, every time a quantum measurement happens, every time there's a choice of outcomes, the entire universe splits. It branches into parallel versions, one for each possible outcome.
Seriously? So if the particle could go left or right?
The universe splits. In one universe, it went left. In a completely separate parallel universe, it went right.
And the observer. I split too.
You split too. One version of you sees the particle go left. Another version of you, in the other universe, sees it go right. All possibilities happen, just in different branches.
Whoa. Okay, that solves the collapse problem because nothing collapses.
It does preserve the maths beautifully. The Schrodinger equation just evolves smoothly forever.
But the cost is an infinite number of parallel universes constantly branching off.
An unimaginable, likely infinite number, yeah. It violates Occam's razor, the idea that the simplest explanation is best. It feels extravagant to posit countless unobservable universes just to avoid the collapse.
Okay, so Copenhagen says measurement collapses it. The Emperor says consciousness collapses it. Many worlds says it never collapses. Reality just splits.
Wow. Those are the big three philosophical camps, yeah. Still debated today.
Regardless of how it happens, the reality we experience is always definite. Let's shift gears now. Let's talk about the actual particles Alice meets. The citizens of this quantum world.
Right, the masked particle ball. And here, the fundamental split is between two types of particles, fermions and bosons.
And this difference is crucial.
It defines literally everything about the matter we see around us. Let's start with fermions. These are things like electrons, protons, neutrons, quarks.
The building blocks of matter.
Exactly. And they are the ultimate individualists.
Because they obey Pauli's exclusion principle.
That's the key. Pauli's principle is strict. No two identical fermions can ever occupy the exact same quantum state at the same time in the same place.
They need their own space. The book says they never compromise.
That's a perfect description. They're fundamentally antisocial in that quantum sense.
And what does that mean for us in the big picture? What's the consequence of that individualism?
It's why matter has structure and takes up space. Think about atoms. Electrons can't all just pile into the lowest energy level closest to the nucleus.
Right, they have to fill up shells, one by one, in higher and higher energy states.
Exactly. Each electron needs its unique address, its quantum state. If they could all crowd together, atoms would collapse instantly.
So this exclusion creates pressure.
We call it Fermi pressure. It's why you can't just squeeze solid objects down to nothing. It's why stars don't collapse under their own gravity, up to a point. It dictates the entire periodic table of elements.
Okay, so fermions build stuff because they refuse to share states. What about the other group, bosons?
Bosons are the opposite. They're the friendly, collaborative ones. Think photons, particles of light, or gluons, which we'll get to, or pions.
And they like being in the same state.
They absolutely do. They prefer it. This tendency is called Bose condensation. It's why you can get thousands, millions, billions of photons all acting identically in a laser beam, same frequency, same direction, same phase. Perfect cooperation.
That's amazing. And their numbers aren't fixed, right?
Not conserved like fermions. Bosons, especially force-carrying ones like photons, are constantly being created and destroyed. Light bulbs create photons, atoms absorb them. They pop in and out of existence as needed to carry energy or mediate forces.
So fermions for structure, bosons for forces and energy transport. That fundamental difference shapes everything.
It really does. Okay, now let's dive deeper into the fermions, to the really fundamental ones, quarks.
Found inside protons and neutrons. Alice meets them at the ball tube, right?
Deep inside, we know they have fractional electric charge, like plus 23 or n-13 the charge of an electron.
Which is already weird.
It is, but their defining feature isn't electric charge, it's something else called color charge.
Red, green, and blue, but not actual colors.
No, just labels for 3 types of a new kind of charge related to the strong nuclear force.
The force that holds atomic nuclei together.
And holds quarks together inside protons and neutrons. This force is mediated by bosons called gluons.
Okay, so gluons are the force carriers, like photons are for electromagnetism.
Right, but here's the crucial difference. Photons themselves don't have electric charge. They're neutral. Gluons, however, do carry color charge themselves. They actually have color and anti-color charges.
Wait, the force carrier also carries the charge it's mediating.
Exactly, and that self-interaction is the key. It makes a strong force behave unlike any other force we know.
How so? What does that self-interaction lead to?
It leads to quark confinement, the most counterintuitive force behavior.
Okay, explain confinement.
Well, with gravity or electromagnetism, the force gets weaker as things get farther apart, right? Inverse square law.
Yeah.
The strong force mediated by these self-interacting gluons does the opposite. Try to pull 2 quarks apart.
The force gets stronger.
Yes. The gluon field between them intensifies, forming these tight gluon cords or strings. It's like stretching a cosmic rubber band that gets harder to stretch the longer it gets.
That is completely backward to normal experience. A longer string should be looser.
But here, the energy stored in the gluon string increases with distance. It takes more and more energy to separate the quarks.
So what happens if you just keep pouring energy in, trying to snap that string and isolate a single quark?
You can't. That's the confinement secret. If you pump enough energy into that gluon cord to theoretically break it, that energy instantly converts into mass following E-NC accord. It spontaneously creates a new quark-antiquark pair right out of the vacuum energy stored in the string.
Whoa. So you don't free the original quark?
Nope. The new antiquark pairs up with the quark you were trying to pull out, and the new quark pairs up with the one left behind. You just end up with 2 new composite particles, like mesons, instead of 1 free quark.
So you can never observe a free quark on its own?
And never. The universe fundamentally forbids it. It's an ironclad rule stemming from the nature of gluons and color charge. It ensures protons and neutrons remain stable, composite particles.
Wow. Okay, so let's try to wrap this up for our listener. We've gone from the Heisenberg bank's weird economy of borrowing energy
Fleeting existence based on uncertainty.
to the compulsory exploration of all paths in superposition.
Everything not forbidden.
Then the whole mess of how reality picks just one outcome, collapse, consciousness, or splitting universes.
A big mystery.
And finally, the social rules. Fermions being individuals, building matter because they won't share.
Pauli exclusion.
And bosons being collaborators, carrying forces, happy to clump together.
Lasers and forces.
And underpinning the matter part, these quarks locked together by self-interacting gluons, impossible to isolate. The quantum world is just built differently. Fluctuation, probability, uncertainty.
It is, and yet, despite how utterly bizarre these rules feel compared to our intuition, QM works. Its predictions are perfect every single time they're tested.
But the conceptual weirdness doesn't go away,
Yeah.
especially with things like entanglement.
Ah, Einstein's spooky action at a distance. That brings us back to Bell's theorem and those experiments, like the ones by Elaine aspect you mentioned.
Right. Remind us what they showed.
They took pairs of entangled particles, photons usually. Entangled means their properties are linked. If one is measured spin up, the other must instantly be spin down no matter how far apart they are.
Instantly.
Faster than light communication would allow, seemingly. They fly miles apart, you measure one, and you instantaneously know the state of the other. The correlation is perfect and immediate.
And this can't be explained by them carrying some hidden instructions from the start.
Bell's theorem proved,
And Aspect's experiments confirmed, that no local hidden variables theory, no secret instructions carried by the particles can explain these correlations. The connection is fundamentally non-local.
Wow. So what's the final thought here? What does that non-local connection really imply about, well, everything?
That's the profound question, isn't it? If the fundamental layer of reality operates with these non-local correlations, this seemingly instantaneous influence across space, what does that mean about space itself?
Yeah.
About information, causality.
It suggests the separated, distinct objects we see are maybe just the surface layer.
It suggests that underneath, reality might be far more interconnected, unified, and frankly baffling than our classical minds can easily grasp.
So next time you touch a table.
Remember, it's enforced individualism, fermions, keeping their distance held together by those bizarre, colorful, self-sticking gluon strings, all built on a foundation of borrowed energy and fleeting virtual particles.
It's existing everywhere and nowhere until you look. The solid world is woven from quantum weirdness. It's quite something to think about.